Bonjour, ladies and gentlemen. Thank you, Hervé, for inviting me here. It's a pleasure being here. I'd heard a lot about Teratec, and I know Hervé for some time. So indeed, really, it's my pleasure and privilege to be here today speaking to you. What I thought I'll do today is give you a quick overview of what we mean by advanced computing from a NASA perspective. One of the things that is important to realize is from a NASA perspective, supercomputing or high-performance computing is an enabling technology. It is not NASA's core business to do high-performance computing, but NASA cannot do its core business without having high-performance computing in-house. So I'll talk a little bit about where NASA is coming from for HPC, and I'll talk about what we're doing in HPC and what the future looks like. I'll keep it at a very high level, but I'll be around at least sometime this afternoon, so I'll be happy to talk to any one of you who might have more detailed questions. So before I get started, I thought I'd give you a very quick overview of how NASA is organized, because this is important. Like I said, HPC is enabling technology for NASA, and so you've got to understand how NASA is organized overall to be able to kind of appreciate what we need in HPC. So aeronautics, these are the 4 mission directorates for NASA. Aeronautics is the first mission directorate. It's the first A in NASA. And aeronautics is mainly focused on, the next generation aircraft, environmentally responsible aviation, less emissions, less noise, how do you manage the next generation of air traffic, as well as autonomy and all of that goes with aeronautics. It is, however, the smallest mission directorate in all of NASA. Given that NASA's budget is about $18 billion a year, aeronautics research is only about $500 million per year. So it's a very small portion of NASA's overall budget. Human exploration and operations, that's one of the biggest mission directorates. The focus is on deep space mission. As many of you know, NASA has decided to transfer access to low Earth orbit to commercial companies. So going to the station and other locations in low Earth will be handled by commercial companies, but NASA will focus more on deep space missions, missions to Mars, asteroids, asteroid retrieval mission. All of that will be the focus of human exploration, both robotics and with humans. Science is another huge part of NASA. And in fact, Earth sciences, surprisingly, is a big component of what NASA does. NASA, being a space agency, has a different perspective of Earth than any other ground-based agency. And so Earth sciences is very important part of NASA's portfolio, but NASA also does a lot of space sciences, heliophysics, astrophysics, and all of that. And then finally, there is space technology. So that gives you kind of sense of what NASA needs in terms of high-performance computing. High-performance computing is just going to be able to enable all of these things. And then if you look at how NASA is organized, many of you already know this, NASA is a large U.S. federal agency, and we are distributed all over the country. Obviously, many of you know many of the more space-oriented centers like Johnson or Kennedy and Marshall, but there are also other research centers, and I'm actually located in near San Francisco at Ames Research Center, where we do a lot of the enabling technologies that allow NASA to do all the things that NASA needs to do. And in fact, high-performance computing in 2006 was consolidated at one center, and that is at NASA Ames Research Center. And I've been leading high-performance computing for the entire agency for the past 8-9 years. So all of the simulations and modeling and analysis that NASA needs to do in any domain whatsoever, whether it be aeronautics, earth and space sciences, or human and robotic exploration, is done at Ames Research Center, and I'm responsible for all of that. So now the question is, the need for advanced computing. I don't think I need to tell that to any one of you here, but the way we look at advanced computing is that these are really digital experiments. So just like you do physical experiments where you might be doing wind tunnel tests or flight tests, advanced computing or modeling and simulation are just digital experiments that can go hand in hand, and you can kind of balance your portfolio. For example, when NASA went to the moon with the Apollo mission, for every 1,000 experiments that we did at that time, right now we are only doing about 1. The rest of it is all done using simulations. But the other part of advanced computing is that it has this predictive capability that you can never have in an experiment, in an actual physical experiment. You are not going to be able to raise the ocean temperatures by 1 degree and see what happens. That is a trivial exercise on a supercomputer. And of course, it can, as we all know, it reduces cost, it reduces risk, and all of that. And from a NASA perspective, there is a huge need for what we call advanced computing. But then let me tell you what I mean by advanced computing. A lot of people think that supercomputing is advanced computing, and supercomputing, nevertheless, is a component of advanced computing. And sometimes on the other extreme, we always think about IT and data centers, and those are HPC as well. The problem with IT is everywhere. It's in your microwave oven, it's in your coffee maker, it's in your car, and so is it in your biggest supercomputers in the world. So everything is IT, so there needs to be a good understanding of what we mean by advanced computing. And so this slide kind of gives you an overview of when we say advanced computing. Obviously, supercomputing is front and center, but there are other things such as accelerator technologies or cloud computing or data analytics or collaborative environments, and even exotic things like quantum computing. And the other thing to realize is that even though all of the big vendors and manufacturers like Intel and NVIDIA and the OEMs are all interested in high-performance computing, at the end of the day, high-performance computing per se does not drive the technology. The technology is being developed or driven for other reasons. Of course, there is a component of HPC, but the challenge always is how do you use these emerging technologies to be able to do what you need to do for your missions. So let me talk briefly about all of these things, but it'll be at a very high level, and I'll just wanted to give you a flavor of all of these things. When we talk about HPC, from a NASA perspective, NASA has 3 requirements. One, of course, is high throughput or capacity computing. So if you look at the top right, NASA does a lot of engineering calculations. If we are building the next rocket, which is called SLS, the Space Launch System, which is going to be about 30–40% more powerful than Saturn V, that took us to the moon, it requires a lot of engineering calculations. So these are aerodynamic database generations where you are creating a lot of databases, both aerodynamics, aerothermodynamics, maybe acoustics. And so these are engineering calculations. So essentially, you're running a large number of the same code with slightly different input parameters to populate a database. NASA also has a lot of what we call leadership or capability computing. For instance, if you look at the lower left, if you're trying to capture a aerodynamic, the rotor flow, the vortices and how the wake gets convected downstream and how it interacts with the blades, that's a big, large calculation. So that's a single calculation that you're trying to run on maybe 70,000 or 100,000 cores, and you want as much resolution as possible, and you want to push that job through. So both these kinds of jobs have to run on the supercomputer. It's not one or the other. And then finally, NASA being a mission agency, a lot of NASA simulations are time critical. So if we have to move the station a little bit because of micrometeoroids, or when we are doing the shuttle, or in future when we are supporting other satellite missions or rockets, then these calculations have to be done immediately. It's not a computer that can be available at some point or is somewhat researchy that it cannot really do these things on a very short notice. So here's one quick chart of what we have in terms of computing, and because of all these reasons, we have a variety of computing capabilities. We, of course, have Pleiades, which is the main supercomputer. It has about 185,000 cores, various generations of Intel Xeon processors. Some of these have GPUs installed in it. But we also have shared memory systems from SGI. These are the ultraviolet systems because some of the CFD codes require large shared memory. But we also are investigating Knight's Corner and eventually Knight's Landing those accelerator technologies. And then we have a hyperwall, which when we built was the largest resolution display in the world. It's connected directly to the supercomputer through InfiniBand, but it's driven by GPUs, and so it allows you to look at calculations in real time. It can be used in two modes. You can look at single large image, or you can look at sets of related images. And the advantage is that because it is connected directly to the supercomputer, you can do what is known as concurrent visualization. So you don't need to run a simulation, store everything into some files, read it back later and do an analysis. You can do the analysis in real time while the calculations are going on. But the other thing also that is important is when you're talking about supercomputing, it's not just the computer itself. That is, obviously, most of you know that already. But from a NASA perspective, you have to be able to provide that capability in-house. So this is kind of a busy chart, but if you try to at least focus on the important circle that is in the chart, or a spiral in some sense, at the very top, you have these various NASA mission challenges. And like I said, these could be aeronautics or science or exploration. And what happens is that these are the calculations that need to run on the supercomputer. The way it works at NASA is that the supercomputing capability is provided in some sense free to these programs and projects, because supercomputing and all of these services are already paid for by NASA at the very beginning. So any program and project that needs to run simulations on the supercomputer do not have to pay for any of the services. It's already paid for. All they have to convince is they have to convince NASA, mission directorates, and headquarters that that is an important project. At the same time, from our perspective, when we are running the supercomputers, we do not have to worry about getting funding from the various programs that are running on it, because we are getting direct funding from NASA top line to begin with. So what we do, though, is we therefore provide these services, whether it be computational scientists, people who help with the optimization and the scaling of codes, porting codes over, with all of the peripheral capabilities like storage and networking and data transfers and IT security, as well as visualization. And it's kind of a spiral, because when you go through this process once, many things come out of that, so that helps the domain experts and the actual scientists and researchers to come up with the next way of doing things. So what I thought I'd show is, because we are in a kind of a technology forum, I wanted to show you a few things that are being done on this system. Again, not going into too much detail. For example, in aeronautics, we are doing a lot of studies with fuel injectors. These are these lean direction injection design, and what we are trying to show is that there is some interaction among the injectors. In this picture, what you're seeing at the top are contours of gas temperature, and the bottom shows the contours of nitric oxide. So the idea is just looking at one injector is not good enough. You have to be able to look at multiple at the same time. We are also doing a lot of work with complex aerospace vehicles. This is using fundamental technologies like adjoint-based mesh adaptation to be able to simulate a transport aircraft in high lift configuration. And so you are using that adjoint method to be able to do mesh adaptation. And then, of course, like I said, rotorcraft simulations are one of the most complex calculations that one could do because of the vortex wake and how that vortex interacts with the next blade, unlike a fixed-wing aircraft, and how it interacts with the fuselage and how that creates high-speed impulsive noise, blade vortex interactions, the stability and the performance of helicopters. So what I thought I'd do is maybe show you a very quick image of kind of the simulations that are going on. These are simulations that are happening on the supercomputers and then getting simulated in real time using concurrent visualization. And this was the first time that we were able to do these using mesh adaptation, doing at least 8 or 10 revolutions, and being able to see the entire vortex structure and develop these figure of merits, which are the most important characteristic of a helicopter simulation, and show how closely they can be matched to experiments. Going along, I thought I'll show you a little bit about space exploration as well, because that's another big area. One, of course, is the Space Launch System. This is going to be the NASA's big next rocket. A lot of simulations about the separation of the solid rocket boosters, whether they separate cleanly from the launch vehicle, questions about plume-induced flow separation, questions about the launch abort system that sits at the tip of the launch vehicle in order to save the crew in case of a catastrophe. So again, these are lots of simulations, but these are simulations unlike the previous simulation where you are running the same calculation over and over again, but slightly different input parameters to design maybe the shape of the nose cone, maybe decide how the engines are laid out in SLS. This is another example of a explosion in a launch pad and trying to understand the safety of an explosion rear test facility and how you would mitigate such disasters. And then finally, as you know, NASA is still committed to the space station at least until 2024, probably until 2028. But one of the problems with the space station is that there are lots of joints and there is lots of fatigue. So you need to calculate all the load points at all these various joints and see how you could replace them, or it's basically what you're doing is system health monitoring and management. One of the things I thought I would show you is this is a simulation of a flame trench. So this is what happens at the first second or two of launch. As you know, after the engines are fired and the plume comes out, the rocket still does not lift off for about a second or so. And during that second, it is very critical how the plume is actually exhausted through the flame trench, how the acoustic waves propagate up of the vehicle, and how these things interact with the launch facility, and how these things might interact or damage any of the payloads that you may have inside the rocket. Again, this is an extreme case because this does not have the water suppression system. This is just assuming the worst case where you have a launch. And then finally, like I said, Earth Sciences is a very big part of NASA. So we are doing these global ocean simulations. These are basically doing data assimilation over the past 50 years, making sure that the models actually agree with observed data, and then how do you use those models to then make predictions into the future. With supercomputers now, and NASA is very interested in doing these large-scale global simulations, both oceans, sea ice, interactions with the atmosphere. For example, one of the other things that we're doing is also cloud modeling. This is perhaps the hardest of all of the components when you're trying to do an integrated weather simulation. For example, in clouds, you must be able to not only model, water, but ice, rain, snow, and even hail. So this is a much more different or a complex problem. And then finally, ultimately, at the end of the day, a lot of the decisions are made at the local level. So you must be able to make predictions and decisions at a much local level, whether it be urban planning, or, for example, this is the Yosemite National Park, or it be Napa Valley wine region. So a lot of the ultimate decisions happen at a much regional scale. But what you need to do is to be able to look at global satellite imagery and be able to do subsetting down to the local scale and make predictions out of that. And then finally, I thought, just to be fair with all of the things that I showed, this is kind of a huge simulation that is going on. This is a 1/48th of a degree global ocean simulation. So this is a high-resolution simulation. So basically, at the equator, we are talking about 3,600 times 48 grid points to be able to do this simulation. So let me stop there, and let me then talk about some of the other components. So accelerator technologies. Accelerator technologies are going to happen whether we like it or not, and there are, at least, as we all know, there are two primary ways of doing it. One, of course, is GPUs. He's going to talk about NVIDIA, what they're doing, and of course, there is Intel. And Intel is saying that their Rmax is more than the GPUs, and NVIDIA says that the top 10 Green 500 machines are GPUs, and Intel says that 475 of 500 are, of course, so that's a very nice competition going on there. But from a NASA perspective, we have to get codes to work. And at the end of the day, the GPUs didn't quite work for us, at least the versions that we had. Because it's not a question of not only porting codes over to GPUs, but how do you make sure that there is a life of those codes, that if NVIDIA were to go away or decide to do something else, what am I going to do with all these codes that I've written in CUDA or OpenCL? And then how do you verify the performance of all these codes in the future? On the other hand, the Intel Phi tells us that all you need to do is recompile the code, and the code runs perfectly. Of course it runs perfectly, except that the performance is terrible unless you pay a lot of attention to do that. And again, there are all these things that you can do. You can run it in native mode, either on the Xeon or on the mic. If you run it on the Xeon, then why do you have the mic? If you run it on the mic, then why do you have an expensive Xeon processor sitting there? If you do it in offload mode, then there is an overhead of transferring the work from the Xeon to the mic. If you do it in symmetric mode, of course, that's perfect, but then you have to do a load balancing of your code to be able to do it symmetric. So this is not a simple solution. And for an agency like NASA, where we have real things to do, it's not a question of writing 5 papers or show some big performance gain. I have to actually fly rockets and land on Mars and Moon and all these kinds of things. So it is a much more a real experiment than just getting some nice curves and all that. So again, I'm not going to go into this, except these are the points that I already made. But again, we are looking forward to the next generations of both GPUs and mics. Knight's Landing will be there, but we'll continue to do what makes sense from a NASA perspective. And at this time, the vanilla Xeons seem to be working just fine for us, and we'll see, and we'll make adjustment when that happens. Have to talk about big data, because if you don't talk about big data, then people think that you're not actually in the modern world, because everyone talks about big data. So how can you be doing supercomputing without big data? So if you look at it from a NASA perspective, NASA has lots of data, both observational data sets. NASA probably has the largest collection of observational data sets. These are freely available to anyone in the world, but NASA also generates a lot of model and simulation data. But the question is, how do you integrate big data in, for our case, big data with big compute and analysis and analytics to be able to support what NASA things are? So, there are all these different things in if you look at it from big data perspective from a NASA's point of view. There's the question of where the data is, how do you manage all the data, how do you develop analysis and algorithms and analytics algorithms. And perhaps the most important thing of this whole exercise is the workflow. The biggest problem that happens now, at least in the science and engineering community, is someone downloads some data from somewhere, does something with the data, and then writes a paper or writes a report. There is no way for another person to come and replicate exactly that. So there is no way someone can either disagree with what this person just did or actually reproduce and take it forward, because that whole process in the middle is a complete black box and no one exactly knows how this is done. So what NASA has been doing is to capture that entire workflow. So one of the things that we have done is called the NASA Earth Exchange. This has become very popular, and in fact it is touted by the White House. You can actually check it out. It's called nex.nasa.gov. And the whole idea is that what we want to do is people talk about SaaS. In fact, I think it was mentioned in Hervé's charts this morning, and S in there is software as a service. But what we are talking about here is science as a service. So because at the end of the day, your data is there, your models are there, and your papers are there. So what you really want to know is what is already available and has been done so that you can actually move it forward. So NASA Earth Exchange is a combination of various things. It has a collaboration portal, so it's like a website. Anyone can get in there. It provides compute resources as well as storage. And it also holds all of the codes that NASA is making publicly available in earth sciences, as well as any other person can put their code on there as well. At this time, we have way too many users that we actually are having a hard time keeping up with this. So one of the things that we have also done is we have an agreement now with Amazon Web Services. So a lot of the compute and the storage is also done on Amazon, and that is a version that is called OpenNEX. So that is more of a pay-as-you-go model, and that is also less restricted by NASA regulations. But NASA has its own version of it, which is called NEX. And here are some of the huge calculations that are going on. For example, you can do really high-resolution climate projections. Some of these are really scary. For example, if you look at the inset, now this is only looking at spring temperatures. Actually, if you think about it, the temperatures in the months other than March, April, and May don't really matter, because March, April, and May decides the harvest and the growing season. So those are the 3 most important months of the year. Everything else is, okay, it's Christmas and Thanksgiving and all that, but it doesn't really matter. So if you look at that, then you will see that two important things. One is the red curve. The yellow part is actual data for the past 50 years, 64 years from 1950 to 2014, and then projection up to 2099. And that shows that the mean temperature in the US is going to increase from 12 degrees Celsius to 15 degrees Celsius. But more interesting is the blue bars, which keeps going down. And the blue bar is actually the 0-degree isotherm. So that says that on average, in the months of March through May, in 1950, 2.5 million square kilometers in the United States was going to be at 0 degrees or lower. However, in 2099, only 0.6 million square kilometers is going to be, the million is missing there, 0.6 million square kilometers is only going to be less than 0 degrees or lower. That is a very scary situation. So, okay, so then let me come to the very last portion of my talk. This is the most exotic thing in all of computing. So again, NASA is leading this effort, not only for, so I'm leading this effort for NASA, but NASA is leading this for the entire federal government. What we believe is quantum computing is perhaps the most exotic and perhaps the most revolutionary thing that can happen to computing. We think that quantum computing does not, at this time in the near future, going to exist by itself, but it's going to be an attached capability to classical computing. I don't know how many of you know about quantum mechanics, but even people who founded quantum mechanics, like Einstein and Feynman, have said that it's the most weird of all sciences. And people have said that if you ever meet someone who tells you that they know quantum mechanics, you should run away as fast as possible, because really no one understands quantum mechanics. It is so counterintuitive, and it violates everything that we know about physics that it's hard to believe that it actually works. But again, this is not a lecture on quantum mechanics, because that's a 4-year college course to understand quantum mechanics. So I'm going to talk about quantum computing very quickly. So the important thing is that quantum mechanics happens at a very atomic scale, at very low temperature, at very low sizes. But the main problem of quantum mechanics, unlike classical mechanics, is every observation changes the measurement. So that is a really bad thing. So here you're going to calculate something, and of course if you're calculating something, you want to read it out at the end, because if you're not going to read out your calculation, then what's the point in doing a calculation? But the problem in quantum mechanics is every time you read, you're going to get a different answer. So that's really bad. And the other thing is that, so it comes with a probability. But that by itself gives you the power to be able to do some things. So at a very high level, if you look at the little picture on the right, if you have these 3 bits, and in quantum they're known as qubits, and a qubit, if you have 3 of them, so basically they have those 8 states, just like a normal bit. But in a normal 3 bits, you would have 8 states, and the 3 bits can be in only one of those states at any one time. So they can be 000 or 001 or 111. So they can be in only one state. So it's a very deterministic situation. So there'll be only one of those states. But if they're qubits, then they can be in all 8 of those states at the same time. So that's a huge power. So that means if I have n qubits, I can be in 2 to the n states at the same time. The only problem is, each time I read it, it'll only give you one of those 2 to the n states, and each time you read it, it'll get a different answer. But if you just think about how powerful this is, if n is 512, and 512 is not a very big thing, because that's a system we already have at NASA, 2 to the 512, if you calculate it out, is 10 to the 153. So here we are talking about exaflops, okay? So that's what? 10 to the 18. Okay, 1,000 exaflops will be 10 to the 21. This is 10 to the 153. Just to give you a sense of how large that number is, the number of atoms, this is the number of atoms in the entire known universe, is 10 to the 82. And so a machine, a true quantum computer with 512 true qubits that can be entangled, can be in 10 to the 153 states at the same time. So it can do all those things at the same time. So again, but what we have is a quantum annealing machine. It's a very special type of quantum machine. It's not a universal quantum computer. What it does is it allows you to do superposition and quantum tunneling. So instead of being at stuck at a local minima, and having to go over an energy barrier, you can actually tunnel through the energy barrier to get to a global minima. And the idea is that since you can look at all possible states that you can go to from a local minima, you can find the global minima faster than any other classical computer could ever find. From a NASA perspective, these are all the question, of course, always comes up, as I said, well, why does NASA care about this? Well, these are all the various applications that NASA is interested in that have optimization as part of this. And it could be, for example, air traffic management. That's a huge optimization problem. Image and data fusion. If I give you a single image of anything, for example, that's an image of some part of the US, you can get a lot of information out of a single image. But if I have 1,000 images of the same thing at different frequencies, at different times of the day, at different seasons, if you could fuse those, then you could get a lot more information out of that fused image. The problem is, if you have 1,000 images, well, how many of you should you fuse? Maybe you need to fuse 4 or 5 of them. And then what are you looking for? You don't even know. So that's, again, exactly where a quantum computer comes in. I'm not going to talk about all of them, but for example, the other thing that we are working on is this fault diagnostics. When things break, things never break suddenly, even though we always think that things suddenly break. My hard drive just failed. Well, that never happens that way. Things are going wrong for a long time before it actually fails. In classical methods, it's impossible to monitor every possible scenario. Because if you could do that, then, for example, that's an actual sensor from the station that shows that before there was a catastrophic failure, there were some things going wrong before that. But what a quantum computer could do is it could actually track all of those potential things that could happen and then make a decision or stop that process before there is a catastrophic failure. You cannot do this in classical computing, but you could do that in quantum computing. But again, this is very early. I thought I'll show you a very quick, this is my second last slide. So I thought I'll show you a little picture of what the quantum computer looks like. I wouldn't call it a quantum computer. I call it more of a quantum device or a quantum system at this time. So this is the D-Wave system. It's a company in Vancouver, Canada. It's a quantum annealing device. So it basically takes a metal called niobium, and if you cool niobium to 15 millikelvin, that's a really cold temperature because interstellar space is 3 Kelvin. But if you take niobium and you cool it down to 15 millikelvin, then it becomes superconducting. And if you make niobium into a little loop, then it allows electrons to flow in both directions of that loop. And therefore, as soon as you have a loop and electrons flow in both clockwise and anti-clockwise direction, you have both an up and a down magnetic field. So right there, you have created a qubit. That means you have created something that can be in 2 states at the same time. And of course, it has to be shielded from the Earth's magnetic field, so that's why you have a big Faraday cage. And it has to be completely free from all transient vibrations, because quantum systems, by definition at this time, are extremely fragile, because they need to be staying in this quantumness state, because they have to remain at the lowest energy state at all times. So they have to be prevented from any excitation to move them into a high energy state. And so what you have is a big black box, which is a Faraday cage. Inside of that, you have that upside-down wedding cake kind of a thing, apparatus that brings the temperature down from 300 Kelvin to room temperature using liquid helium to at least 20 millikelvin. We run it at 15 millikelvin. At the tip of that is the processor, which is the Vesuvius processor. It has 512 qubits. And every calculation, it doesn't matter what you calculate, every calculation always takes 20 microseconds. That is known as the annealing time. Whatever you do, it takes 20 microseconds. What you have to do, though, is you have to run the same calculation hundreds of thousands of times to get a probability distribution to get the final answer. So again, with that, I'm going to end. But again, the main focus of NASA is to enable science and engineering that NASA needs to do in order to meet NASA's missions and goals, whether it be looking for planets, moving asteroids around into lunar orbit, supporting national disasters. But the idea is that you do that through both high-performance, productive supercomputers that are actually working and not some research system that might be #1 in the world but has to work, as well as always paying attention to what is coming out of the technology roadmap from companies, from the semiconductor world, to be able to leverage that to meet NASA's requirements. And with that, I'll end. Thank you very much for your attention.
Thank you, Rupak, and thank you for this very extensive presentation.
Okay, thank you.